Now let's take a closer look at the magnetic field produced by a loop carrying some current I. And as a reminder, let me write our right-hand rule for loops at the top here. So the right-hand rule for loops says, curl your fingers, specifically your right fingers, in the direction of the current, and if you do that, then your right thumb will point in the direction of the magnetic field inside the loop. So what we have down here in example 1 is a figure of a loop held on its side. And this figure is pretty confusing, but the idea is we have a loop like this, and then if we rotate 90 degrees, then it looks something like what we have over here on the right. And for this figure, at the top, we have a dot which signifies the current for this loop is coming out of the page. So current comes out of the page at the top part, and then at the bottom, this X signifies that the current for our loop is going into the page. So knowing this fact, what I'd like you to do is pause the video and use your right-hand rule for loops to draw the magnetic field produced by this loop shown in the figure. So you'll be drawing magnetic field lines for this loop. So if we were to curl our fingers so that our fingers would point out of the page at the top of the loop and then curl around and point into the page at the bottom of the loop, our thumb would be pointing to the right. That means that the magnetic field on the inside part of our loop is directed to the right. And so if I were to draw some magnetic field lines, they would look like this. So there's our field going through the loop, directed to the right, and we can draw some more field lines like this, a couple more, and then make sure we add our directions. So now if I were to zoom in and just look at the magnetic field here, and I told you, here are some magnetic field lines, and to the left, not shown, is some object. And I told you, hey, it's a bar magnet. Would you tell me that the part that I'm not showing you is a north pole or a south pole? Go ahead and pause the video, figure out your answer before continuing. Our convention is that magnetic field lines leave the magnet at the north pole and go into a bar magnet at the south pole. So, but on the other side that's not shown, you tell me, hey, it's a north pole. If instead I were to show you just this picture, ignoring the figure I drew on the left there, and we were focusing just on the magnetic field lines on the right side of the screen, and I told you what's on this side that I'm not showing you, is it a north or a south? What would you say? Well, we know south has magnetic field lines pointing towards it, so you'd say it's a south pole. But wait, actually, in real life, it's a loop. And so what we see is that on one side of our loop, it looks like a north pole. On the other side of our loop, it looks like a south pole. So it turns out that the magnetic field for a loop of current is very similar to the magnetic field of a bar magnet, where remember, if we have a bar magnet, here's our south pole, here's our north, our magnetic field lines exist in loops that leave the magnet at the north, go in at the south. And so what we can say is that a loop of current creates a magnetic field that looks like that of a bar magnet, and it doesn't just look like a bar magnet. A loop of current actually acts like a bar magnet. To determine which side of the loop is the north side, we can use our right-hand rule. Our right-hand rule for loops, says to curl our fingers in the direction of the current, and then our thumb is in the direction of the magnetic field inside the loop, and we can add on to this, our thumb actually points on the side of the loop that is north. So thumb is be inside the loop and points to the north side of our loop. So if this is our hand over here on the right and we're curling our fingers in the direction of the current, our thumb then points north. So now in the examples below, what I'd like you to do is, using our right-hand rule for loops, determine the north and south pole for each of the loops shown. Then, using what you know about bar magnets, that is, like poles repel and opposite poles attract, determine whether or not the loop shown will experience an attractive or repulsive force. So in the first example on the left, using our right-hand rule, we know that the right side of this loop would be the north and the left side would be the south. So what I did there is I curled my fingers out of the page at the top part of the loop into the page at the bottom of the loop. My thumb points to the right. That means the right side of the loop is north, the other side is the south. The other loop in this example is an exact copy, which means this is a south, that's a north. If we look here, we have a north and south near each other, and we know that in those situations, there will be some force that causes our two loops to attract. In the example in the middle, well, the first loop on the left is an exact copy of what we just did, so that's a south and that's a north. And now for the loop on the right, what I'll do is I'll curl my fingers into the page at the top part of the loop, then wrap them around so they point out of the page at the bottom of the loop. My thumb right now is pointing to the left. That means the left side of the loop is a north and the right side is a south. Looking in the middle here, I see two norths near each other, and we know that in those cases, our objects will repel. So there'll be some force that would cause our two loops to repel. And in the last example at the right, again, curling my fingers into the page at the top part of the loop, out of the page at the bottom, my thumb is pointing to the left, so the left is our north side of the loop, the right is the south. We have two south poles near each other, so these objects will repel as well.